All right, so today we have Zhi Huang. He is a postdoctoral student at Stanford University, and in August 2021, he received a PhD degree from Purdue University, majoring in electrical and computer engineering. His background is in the area of artificial intelligence, human AI collaboration, digital pathology, and precision medicine. Recently, there have been breakthroughs in foundation models and generative AI present with exciting opportunities for transforming the healthcare landscape. And in the seminar, Dr. Huang will share how to train a visual language foundation model for pathology using publicly available medical images and how that publicly shared medical information can be harnessed to enhance diagnosis, knowledge sharing, and education. And he will discuss the benefits of human AI collaboration across two diagnosis tests. Without further ado, Dr. Hong.
Thank you for the introduction, Hector. So it's my honor to be here and to have my presentation at Sunbelt Spatialomics Seminar. And my title is Visual Language Model for Digital Pathology and Clinical Decision Making. Well, let's get started. So in this talk, I will firstly, I think this talk I'll be dividing the talk into two parts. First is I'll introduce how visual language AI can help us in analyzing spatial omics data. I will start first introducing how we harness the internet data and train the foundation model for pathology, and then let's explore what is the possibility of using that model for image searching in spatial omics data. And the second part is how we can actually leverage the spatial omics knowledge for our clinical workflow and developing the next generation of AI model for digital pathology. And we believe there's a tremendous resources and opportunities behind it. And we are excited to see how this can move forward. So with that, let's first dive into the part one, which is a visual language foundation model for pathology. So it was published in Nature Medicine last year. With that introduction, I will also briefly go over its relevant application to spatial omics. Here's one of the example I'm going to show later. Okay, so before we step into that detail, there's a little bit background about why this is very important to train the vision language model for pathology using public data. As we all know, machine learning requires a lot of data to train. For example, ImageNet typically has more than like 14 millions of data. And in Lion dataset, we have more than 5 billions of images and text pairs. But computational pathology does faces the barriers. There are so many different disease types, so many different differential diagnosis results. And we really have a limited data sets with careful labeled in natural language, right? And so that becomes a problematic issue when we want to train a pathology model for all different purposes. But at the same time, there's a tremendous amount of knowledge shared by thousands of clinicians over the public forums such as Twitter and Wikipedia and over other public internet places. And we realize that this information carefully annotated, spontaneously annotated by those clinicians could be a valuable resources that can be leveraged and train a general purpose medical AI, which can benefit our clinical study and research. So with that, we created open paths from Twitter and other public sources by selecting 32 different pathology hashtags, such as neuropath, breastpath, and so forth, provided by based on the US CAP 2016 pathology hashtag guidelines. And then we perform a very stringent cohort inclusion and exclusion by cleaning up the data and remove a lot of noisy information. For example, we only keep the Twitter description text written in English and remove the retweets and the sensitive tweets. And in addition, we also including the Twitter reply with the most likes because we believe those comments with most likes also may contain more or less relevant medical knowledge within the image that they provided. Furthermore, because we believe when people start posting a question, that question, that sentence may not really containing any useful or accurate medical knowledge. So we also remove those sentences with question marks. And we further follow up with a additional text cleaning, such as the removal of emoji and hyperlinks. So at the end of the day, what we get is an example image and text pairs for each Twitter post. So one of the example tags is like small infiltrative looking glands with crystalloid secretions are suspicious for prostatic adenocarcinoma. And the beauty of annotating a pathology image patch, a little image patch, not whole slide image, is the beauty of that is we can annotate with a lot of medical knowledge into it. At this example, we not only tell the machine that this is a prostatic adenocarcinoma, but we also mention it contains several small infiltrative looking glands with crystalloid secretion. In some other captions, it may also contain the location information, such as neoplastic cells are forming a cluster in the upper right. Those information are really useful for a model to learn the spatial textual information and try to connect those two information together, right? And so later on, we get a bunch of that kind of image text pairs. But as we extract those image and text pairs from the Twitter or currently X, there's definitely going to be a lot of noisy data. For example, we try to pull out the data given the pathology hashtags, but those hashtags may also constantly used during the conference. And during the conference, the clinicians may also post selfies or PowerPoint slides, and that is not so specific to a medical knowledge. So we further train a pathology image classifier to remove those non-pathology images. And at the end of the day, we curated 16 years of knowledge all the way from 2006 to 2022 with over 208,000 high-quality image text pairs. We also performed a manual data inspection, suggesting over 98.5% of the images are actually relevant to the pathology image and knowledge. So by the time we published this work, it was the largest public pathology visual language data sets. And benefit from this huge amount of data, we now want to explore what is the potential of leveraging that data to train a general purpose medical AI that can helping us to perform a lot of different downstream tasks. Just to mention, those medical image text pairs are not only coming with H&E image and IHC image, it may also comes with some immunofluorescence images or codex images. Although I don't think that would be that much, but it's definitely including those image text pairs. And that can be really helpful in our downstream analysis. And so once we have the paired image and text, here's an example. We put the image into an image encoder, in this example, a vision transformer. And we also put the text into the OpenAI Clip Models text encoder. So we can then output image into a vector space. We can project the image into the vector space. In our example, our vector space is with dimension 512. And similarly, we also project the text, the sentences into the same dimensional space, which is also 512. By projecting those image and text into the same dimensional space, we can then using the contrastive learning to compare the correlation between the paired and unpaired image and text. So the beauty of this contrastive learning and the clip-like model is that we can encourage a higher cosine similarity on the diagonal, which is a paired image and text, and encourage a lower cosine similarity, impose a lower cosine similarity of the diagonal through the training process. And over the iteration, the model will get learned, okay, if the image and text are coming from the same Twitter post, then we should map those image and text together along this diagonal. So the model will better align those two different data modalities. So that's the basic idea of how the contrastive learning is used in this setting. So we feed all our input data, 208,000 image text pairs into this model. And by training the contrastive learning laws, finally, we come up with our model named PLIP, which stands for Pathology Language Image Pre-training Model. So PLIP is a versatile foundation model for a lot of different downstream tasks. So I will first introduce how the PLIP model we trained from the public resource can be used for academic research. And then let's discuss how does the PLIP model can be used for educational purposes, such as image retrieval. So now let's first focusing on to what extent the model trained on medical Twitter can be useful and how well it can understand the basic pathology knowledge. So we start evaluating by the zero-shot classification. So the definition of zero-shot class learning is that once the PLIP model trained on OpenPath data, we can then apply the model to external data set with any downstream target task. And the target task can be distinguishing different tissue types, such as distinguishing the tumor, adipose tissue, lymphocytes, stroma tissue, and so forth. Or like we can perform a binary classification, like distinguishing whether its image patch is benign or malignant. Or we can also distinguish different cell types, such as neuron, astrocytes, oligodendrocytes, microglial, those neuropath cell types. So, but just to keep in mind that since the image and text pairs is trained on Twitter and is extracted from Twitter, and those images are most of the time those images are pathology image, small image patch, which is representing a small region of interest. So we perform the evaluation. We also perform the evaluation on the region of interest level. So the beauty of zero-shot classification is that we can directly apply that zero-shot model to any different new data set with any arbitrary number of classes without further training to just see the ability of it, how well it can understand the basic knowledge of pathology. So here's a demonstration of how the zero-shot learning has been used for evaluation. So if we input an image into the image encoder, we definitely get an image vector, right? And we also can input a list of text candidates, such as an H&E image of tumor, an H&E image of lymphocyte, and so forth. We put those text input candidates into the text encoder and returns a list of text vectors. So we basically compare the source image vector with a bunch of text vector candidates. And so the one with the highest cosine similarity should be the one that the model suggests. And in this example, the model will suggest the correct answer should be an H&E image of tumor. So we evaluate the zero-shot learning ability across 4 external validation data sets, focusing on colon data set, pan-nuc data set with 19 different tissue types, and DigestPath and lung cancer data set, lung adenocarcinoma data sets for benign and malignant tissue identification. And we found that using PLIP model can achieve a lot better than the CLIP baseline model, suggesting the model is getting learned from the public knowledge, which is in this case, medical Twitter. If we further look into the confusion matrix of the cathode column data set, how well the PLIP model can predict those 9 different tissue types, we can find that PLIP model is especially doing good in distinguishing adipose tissue, the colorectal adenocarcinoma epithelium, and lymphocytes, and normal colon mucosa, and smooth muscle. And it does perform not so well in several different classes. For example, mucus and or debris, right? Those two are typically, most of the time, clinicians may not mentioning that much in the Twitter post, which is not surprisingly, those two are not well predicted. But if we further look into the UMAP plot of those 9 different tissue types, we encode after the image encoder, we project through the UMAP and we can see how well the PLIP model is able to distinguish those 9 different tissue types, suggesting the ability of the PLIP model can helping us to find out the different tissue, the differences between tissues. So that's about the zero-shot classification. And Well, we found that zero-shot classification can be very helpful, especially you can provide any arbitrary number of classes for identification. But we also observed that the performance of zero-shot classification is not so accurate, right? So in this example, Kessler-Collin dataset, the F1 score is like 0.56, and the Pendic dataset is 0.65. It does perform a lot better than the baseline model, but it's still really premature for it can be used in a clinical or research setting. So basically, the zero-shot learning is just to see how well it can perform without any additional modification for various of downstream tasks. But if we really want to train, if we really want to have a specific model that is really accurate for a specific downstream task, we can then perform a transfer learning. And our experiment suggesting that using the pleb model learned from the internet data is actually a performed vision encoder that can be used for the downstream transfer learning tasks. So the definition of transfer learning is pretty much the same as the definition of zero-shot learning. Basically, we train on the open path and apply to external data sets with any different target task. But the difference is that in transfer learning, we will further train the data with additional data from the target task. And given that additional data points, the model will quickly understand what is the purpose of the downstream task. And by hypothesis, using transfer learning on a pre-trained model will perform a lot better than training a model directly from scratch, right? And now let's see how well does the transfer learning works in this setting. So the basic idea of transfer learning in this figure diagram is that given a lot of input image, we let the image encoder being trained by the label. And we are actually not only updating the linear classifier, but also updating the entire image encoder. And here's an example of a lung adenocarcinoma data set. And now we can see how well the pre-trained model on OpenPath can surpass the baseline model vision transformer-based model. So just to keep in mind, the pleb model is also having the exact same structure of the vision transformer-based model, but the pleb model is pre-trained on OpenPath, while the vision transformer-based model is pre-trained on ImageNet. And we found that if we only use 1% of original training data, the pleb model can easily achieve the weighted F1 score equal to 0.82 compared to vision transformer base equal to 0.64, suggesting the model pre-trained on OpenPath will achieve a lot better performances compared to the model pre-trained on ImageNet. And this observation is also consistent across all 4 external validation datasets. They can all achieve a very, very high F1 score, such as 0.80, 0.9997, or similar performances. And so the takeaway message is that in the future, if we want to train a image patch classifier to distinguish different tissue types, it is better to train your model through the pleb image encoder, which will most likely give you a much more improved performances. And now we also provide the GitHub link to the pleb model. So you can easily install the pleb model through the pip. And then you can try loading the pleb model in just 2 lines and embed your own images into an image embedding. So this is pretty straightforward, and you can enjoy it on any Anaconda environment, any platform. I mean, yeah. So so here's another code example of how do we use the pleb for transfer learning. I've wrote a really nice package, I believe. So you can basically just import the pathology foundation and then call the pleb model and just load the data and use the fine-tuner class to fine-tune your own model for your own specific image data sets. And the training is actually super straightforward. It's just like how you train a typical sklearn image, sklearn classifier. And the GitHub link is also available right here. Okay, so we have introduced how the PLEP model can be used for research setting, especially on distinguishing different tissue types in image patch level. And now let's see how does the PLEP model can be used for educational purposes, especially for the image retrieval, and how does that can be used for retrieving the spatial omics images, right? So we first start with the text-to-image retrieval. So the definition of text-to-image retrieval is that we can input a text or a sentence such as normal colon mucosa in colorectal H&E tissue. And the text can then fit into the text encoder, becoming a vector. So the vector will then compare all the image vectors in our database. And the one with the highest cosine similarity should be the one that's really close to your input query. So in this example, this is the one that related to our input text. So here's another demonstration. You can also search breast tumor surrounded by fat. Here, the most relevant image in our web demo is also showing this image as an example. We perform a quantitative analysis suggesting that PLEP is the state-of-the-art model to achieve the relevant image patches through the text-to-image retrieval. And so, so the last part is image-to-image retrieval. Similar to the text-to-image retrieval, user can ask input an image into the image encoder, and it will encode into an image vector. And we just basically compare all the cosine similarity between image and image. And that can greatly streamline the effort of searching the image in the whole slide image level by manually. And here's an example. When we input a image patch featured with a lot of mitosis, the most relevant image in our database also retrieved images featured with mitosis. And so I think the image-to-image retrieval is really, really useful, especially considering a lot of clinicians when they make a diagnosis in a clinical workflow. He or she may often compare their images into previous example or the cases they have went over before. And image-to-image retrieval will be just as useful as Google search to help you retrieve the relevant previous cases, or those cases sharing the similar tissue patterns or like the morphological pattern of the cell. So that can be really useful, right? And we perform the quantitative analysis compared with three different actional validation data sets, focusing on 9 different tissue types, 19 different organ types, and 24 different staining styles, all suggesting that PLEP model was the state-of-the-art model in the image-to-image retrieval. And now the search engine is also available online through our website. You can try it by yourself. But just to keep in mind, the image search utilize our database of OpenPath, which contains a lot of image and text pairs from the Twitter. And that OpenPath dataset is not a really complete set of everything. Several organ or tissue in Twitter, there may be few people discussing it. So in that case, the image retrieval may not perform so well. So really, that retrieval is really based on how well the data set is established and how many different rare or difficult cases are included in the data set. And in the future, we anticipate we can make a further improvement on the image retrieval by expanding our knowledge set and also improving the vision encoder as well. So when we have introduced the PLEP model for academic research and the educational purpose, especially the image to image retrieval. Here are some actually successful industrial applications for spatial omics data. And here's an example that Enable Medicine published in Machine Learning in Computational Biology in 2023. In this paper, they try to use the PLEP model to query the image patch from their codex data. and their codex data is diabetic kidney disease. So in this example, they try to query the class 2B image patch. And here is all the retrieved patch example within this region A. And what I found really exciting in this paper is that they actually performed a comparison between the plot fusion model they proposed and the random retrieval. And they found that using the plot fusion can be really accurate, can accurately retrieve the relevant class 2B image patches compared to the random retrieval, suggesting the specific ability of plot model to retrieve the relevant image patches, which is also work for spatial omics data. And a few days before, I also tried the plot model for image retrieval in several spatial omics data sets. And here's an example of human pancreas analysis program, HPAP samples by Codex. I randomly pick three antibody channel and see how well I can input a query image and how well it can retrieve the relevant image patches. Well, I'm not really an expert in spatial omics, but I personally feel like the top 10 most similar results reveal a very close pattern to the query image I input through the plot model. And here's another example with much more green channel in the query image. And another example featured with a lot of cytoplasmic information in red channel. Okay, so the conclusion is that PLIP is a foundation model for pathology research and education. Since we released, it has been downloaded, it has been really popular in both industry and academia. And it is right now the top 8 most downloaded PLIP-like model in Hugging Face with over 300,000 downloads in last month. And successful industrial and academic application includes the PLIP fusion search proposed by Enable Medicine Spatial Omics Company, and in Tang et al.'s CVPR 2024, they also propose a PLIP host-like pre-trained model, suggesting using that can perform a lot better than other model backbone. Well, so the vision language foundation model has been really popular, especially for digital pathology, and except PLIP model, which was one of the first publication in last year, there are a lot of very fantastic research also coming out these days, such as the Dr. Faisal's lab, the Uni and Conch models. They also use the DynoV2 and other foundation model and pre-trained on their own data set, suggesting a really compelling results. So we're really excited to see this area moving forward, and we're really happy to see how our open source model can be utilized in both industry and academia. So so that's the conclusion of the Visual Language Foundation model and the PLIP model. Okay, so we have finished the part 1, how the Vision Language Foundation model, such as PLIP, can help us in analyzing spatial omics data, especially for image retrieval and fine-tuning a image classifier. And now I'm going to give a second part talk on how we can actually benefit from spatial omics knowledge into our clinical workflow and our AI pipeline. So in this work, I'm going to share our latest paper, which has just been accepted in Nature Biomedical Engineering. So this work is human AI collaboration framework enhances digital pathology, diagnosis, and accuracy and efficiency. So in this work, we realized that when we propose a model or a deep learning package, it sometimes can be really difficult for clinicians to utilize it without any additional coding or like package installation. And so we realized it is really a good opportunity for us to propose a human in the loop AI framework so that clinicians can use that without any installation or coding requirements. So first of all, I want to introduce how this human-in-the-loop AI framework works. So after the whole slide image getting scanned through the digital scanner, we perform a nuclei segmentation automatically. And then our pipeline is able to extract over 150 features, such as 46 color and morphology features, 32 different textual features, 44 spatial information, and additional 32 deep learning pre-trained features. Using that, we also actually proposed a novel approach to profile cell features, such as the features in both Cartesian coordinates and features in polar coordinates. Using that features, we can allow clinicians use nuclear IO to quickly annotate their own data sets in real time. And here is the real-time demonstration of how the nuclear IO is being used by the clinician. In this example, we invite clinicians to create two classes for the cell for the nuclei. One is neoplastic cell, one is a non-neoplastic cell. And so the pathologist can simply crop a region of interest and mark those cells as tumor cells and mark the rest of the cells as non-tumor cells. Upon each annotation, the model will get learned very quickly in nearly real time, and it can provide you a real-time response. So over the iterations through the active learning, we can actually greatly accelerate the annotation efficiency. So that's the purpose of providing a very user-friendly graphical user interface for clinicians to annotate their data and use that data for subsequent clinical study. So given that software, I want to give a brief demo of how we can achieve that in real time. If you can see my screen, I opened an image, whole slide image, with two nuclei classes created. One is tumor, another class is other. I have not annotated any cell so far, and I'm going to scroll into a specific region of interest. For example, at here. And what I'm going to do is to highlight those cells, and I'm going to try annotate those region of interest, mark them all as tumor cell. So upon my annotation, you can see there are 51 tumor cells I have just annotated. And if I further annotate those as non-tumor cells right here, which is those connective cells, you can see the model is actually getting updated in real time. It's actually learning something. However, it is not actually doing that so accurate. A lot of lymphocytes were misclassified as neoplastic cell. Upon this real-time feedback, you can further correct those model output by marking them as other cell types. So by iteratively teaching the model, we can let the model to perform much better and better over iteration. So after several iterations, we have annotated over 155 cells. And simply with those 155 cells, we're able to achieve a very good performances in distinguishing those tumor cells, right? And there are some false positives. So what I can further do is further mark this as non-tumor cells, and the model will further get learned in nearly real time, and it will getting smarter and smarter. And now the model is really, really specific to the tumor cells. And as you can see, I can quickly and easily establish a binary cell classifier within a minute. And it can further apply to the rest of the tissue. Here, we haven't seen those germinal center lymphocytes so far. So I'm just going to further correct those cells and mark them as non-tumor cells. So after that, the model will understand what is the tumor cell, what is the lymphocyte, what is the connective tissue, what is the germinal center cells. And using that strategy, we can quickly establish a whole slide image nuclei classifier, and the classifier can highlight those those abnormal tissue in nearly real time. So that's the beauty of nuclear I/O. And given that beautiful software, we want to know that to what extent the human AI collaboration can outperform the performance of human alone in digital pathology workflow, especially how well the clinicians can make a better diagnosis through the nuclear I/O human AI collaboration, right? So by trying to evaluate or understand that hypothesis, we evaluate the impact of human AI collaboration through two experiments. So for both experiments, our study design is we invite clinicians, which we randomly assign them either in order 1 or order 2. The order 1 will be assisted by the nuclear I/O classifier. The other 2 will be unassisted, just like looking at whole slide image without any additional overlay of the AI suggestion like that. And the other 2, we basically alternate the order. For those in assisted mode in order 1, now goes to unassisted mode. And after 8 weeks washout, we invite the clinicians to revisit all the cases they have went over before. But now, in this time, we basically swap the order. The clinicians, they previously went into order 1, now goes to order 2. So for each model, so for each whole slide image, each clinician will inspect the image twice, either with assisted mode and unassisted mode. Using that, we'll be able to understand what is the differences between AI assisted and AI unassisted in clinical workflow, right? So we performed 2 systematic user studies at Stanford Medicine. And the first user study is focusing on plasma cell identification in endometrium biopsy. And the second study is colorectal cancer lymph node metastasis identification, which is what I just demonstrated right here. So what I just demonstrated is the second study, colorectal cancer lymph node. Well, let's first dive into the first study, plasma cell identification in endometrium biopsy. So our purpose in this study is trying to understand how we can use AI to highlight the plasma cell. Plasma cell is a gold standard. The existence of plasma cell is the gold standard of chronic endometritis, which is the cause of infertility or failure of pregnancy. But finding the plasma cell is extremely difficult and tedious. It usually only contains 0 or 3 plasma cells out of millions of cells in a whole slide image. So finding a plasma cell is just like finding a needle in a haystack. Really tedious, really time consuming. And most importantly, a lot of time clinicians may miss it, right? Introducing false negative. And so in our system, in our graphical user interface, our AI model trained by 2 clinicians is able to suggest potential plasma cell in upcoming whole slide images, given a clickable gallery. So users can easily click on each potential plasma cell and further verify it in the whole slide image canvas, in this main canvas. Upon the final verification, we invite the clinicians to answer several questions when they finish each inspection of each slides. The first question is there any plasma cell you have observed? And if so, how many plasma cells? And the second question is we ask, do you need to still request CD138 to further confirm your answer? So CD138 is a type of immunohistochemistry can highlight the plasma cell, but it is not only specific to plasma cell. It can also highlight the epithelium cells, the epithelium tissue. So the final diagnosis is all still coming from the H&E. And we found that using AI to assist the diagnosis can double the sensitivity and improve a lot for accuracy as well. And we also found that using AI to assist can greatly reduce the uncertain diagnosis when the clinicians click, I'm not sure. Using AI to assist their diagnosis, the I'm not sure button will be clicked a lot lesser than without using AI. Additionally, we found that using AI to assist their diagnosis there will be a lot lesser additional CD138 requests. Requesting immunohistochemistry may introduce additional up to 1 day turnaround time. So given AI model, we can greatly reduce the turnaround time and eventually introduce a better diagnosis. And furthermore, we found that because we record all the user activity, such as the screen time, so we can actually compare the total time they spend on each whole slide image. We found that using AI to assist their diagnosis can reduce 62% of the time, which also suggesting AI can make the diagnosis faster. And so the plasma cell classifier was annotated and trained by 2 clinicians in 3 hours using nuclei. And the same strategy can be also applied to neutrophils and mitosis and so forth. So we have introduced how the nuclei AI human AI collaboration framework can be used for highlighting the difficult cell types. But how about each individual, they build their own model from scratch? In this example, we invite 8 clinicians to build their own model from scratch within 2 hours, and then immediately apply to 25 cases with over 137 lymph nodes. In this study, we try to see how well they can distinguish the potential lymph node metastasis in colorectal cancer. So in this study, we have 616 lymph nodes. Most of them are negative, but few of them are either micromass, macromass, or isolated tumor cells. So the most challenging one is isolated tumor cells. It can be a really tiny cluster of tumor in a healthy lymph node, but it's actually positive. So in this example, we can see the AI can, after the annotation, the AI can help you highlight the suspicious lymph node, just like what I just demonstrated right here, right? So we found that in our experiment, we found that using AI to suggest the potential lymph node metastasis, we can improve both the sensitivity and true positive for all different positive tumor cells classes, such as especially the improvement is especially large for detecting isolated tumor cells. To get a feel of how difficult to find the isolated tumor cells, here's an example. From the whole slide view, it is barely impossible to tell this cluster of cell is positive unless we zoom into 80 magnification. We can then find there are a dozen of cells. Actually, there are neoplastic cells, potentially. Without AI to highlight those suspicious regions, it is actually nearly all clinicians miss that potential isolated tumor cells. So because we build the software, we also record the entire user behavior, such as the mouse movement and keyboard activity. And we actually especially compare how much time each clinician spent on each single lymph node. And we found that using AI to support and to assist their diagnosis, we can save up to 33% of time on ruling out negative lymph nodes and up to 29% of time on finding out positive lymph nodes. And that time improvement is especially more significant when the magnification is higher. For example, for isolated, I think one of the best example is micromass. We found that without AI assistance, clinicians averagely take 16 seconds time on magnification larger than 4x. But with AI to assist, we greatly reduce their time from 16 to 11 seconds, suggesting using AI can reduce your time in inspecting the detail of the tissue. So the conclusion is that human AI collaboration for digital pathology diagnosis can lead to better and faster diagnosis. And now the nuclei.io is also fully open source. You can install the nuclei.io software, or you can also run our feature extraction pipeline, including the cell segmentation and feature calculation. Everything is readily available in our code base. And the installation is very simple. Just create a new conda environment and install all the dependencies in 3 lines. And then after that, you can enjoy using that nuclei.io software on your own database, on your own host image. It's very simple. And so what about the spatial omics data, right? We've been working really hard on how we can further use nuclei.io, this open source platform, to further improve our understanding or utilizing that information from spatial omics to achieve a better annotation. And one of the future projects I'm envisioning is that if we have a paired H&E and codex image, we can actually extract a lot of new useful cell features, and that can be used for faster and better cell annotation and better cell type understanding. For example, it may be really difficult and challenging to distinguish B cells and T cells from the H&E. So for clinicians, it is really difficult to annotate it in nuclei.io. But if we have the codex data available, it can be providing an additional color channel to helping us to distinguish different subtype of lymphocytes. And so that's what I can see the beauty of using spatial omics data combined with H&E in the nuclei.io platform. So please stay tuned. Okay, so I think I have finished all my part 1 and part 2. And so this is the last slide. I want to envisioning my future research interests. And I'm also looking forward any potential collaborations between our fantastic spatial omics leaders in this field. So in my understanding, the AI can transform the healthcare industry in the future with much more downstream application and even in the basic science. But one of the difficulty we want to tackle is that medicine by its nature, first of all, is multimodal, right? When we talk about biomedical data, we have genomics information, proteomics information, metabolite information in tabular format. We also have pathology image, radiology image in image format. And we also have a clinical report and EHR in natural language format. Those different data modality is actually not only a really challenging task, but also a very exciting field for us to combine them together. And my long-term vision is that we may be able to build a multi-model biomedical foundation model that can understand and decipher disease mechanism and heterogeneity, or simply correlating one data modality to another in a better understanding. So that's my overall vision. Especially down to the downstream classification task, the biomedical knowledge and concept is really abundant in textbook and internet. Not even mentioning there's a differential diagnosis tree with thousands of disease classifications. So there's a way to go for us to build a much more powerful model for biomedical data. So with that, I would love to happy to take any questions, and thank you very much for having me. Yeah, thank you.
Thank you, Zhi, for this exciting and very visual talk. Appreciated the language models that you presented today. So are there any questions from the audience?
So the first is the most stupid one. How did you organize the sperms or the spermatids to look like thank you?
Oh, yes. This is also benefits from a AI model called DAL-E3. This is from GPT. Yes.
So it's a generative data. Oh,
yes.
Nice.
Wonderful.
No,
So do you have any questions?
Yeah.
So yeah.
Yeah. So this is really cool. Again, I'm one of those ignoramuses who don't know anything about coding, but really like the idea that you presented about the human AI interaction and assistance. Clearly, this is an area that needs to be developed further. And again, I'm not inviting myself for a collaboration, but I think these are the areas, and you have rightly chosen to select pathologists that are local. But I look forward to seeing more coming out from that kind of data, because that is really extremely useful. Searching for those stupid plasma cells is not an easy task in the endometrium. I'm just repeating it for people who don't know the stupidity of the whole process. It is a time-consuming, labor-intensive task. So clearly, finding solutions such as what you have proposed is good. It just, we need to have many more such tasks that are automated. But really enjoyed, and I look forward to reading your Nature, the paper that has just been accepted.
Thank you. Yeah.
And we have one
I'm
question
sitting
in the
with my
chat.
microscope. That's what I do. So you realized that you're providing an answer to my pain. So thank you.
Oh, wow. Hopefully,
So
yeah.
yeah, he's already in the loop, basically. So we have one question in the chat. It says, can multi-channel fluorescent image be analyzed in nuclear IO? Thanks so much. Such a great project.
Yeah, so this is a great question, Dr. Mohammed. So the basic idea of nuclear IO is we provide a very user-friendly AI platform, so people can easily analyze their own pathology images. And that pathology image, host line image, can not only be H&E image, but also IHC image. And actually, because nuclear IO is purely written in Python, when we read the data, we actually use the OpenSlide, that Python package. And in terms of the multi-channel fluorescence image, if there's a package that can be used in Python, I'm sure there's a lot of package. For example, analyzing the codex data, we can use TIFF file. Those package, we can read the image patch, and we can replace that part in that open source nuclear IO. In that case, you will be able to analyze the multi-channel fluorescent images. Yes.
Wonderful. I think we have another question from TN. Do you envision further developing the H&E-based nuclear segmentation to segment whole cells, nuclei plus cytoplasm, from an H&E image? I imagine such an algorithm would be super helpful for Visium HD datasets.
That is a great question. So the nuclear IO package is the nuclear IO is an AI platform, and the specific cell segmentation algorithm we utilized is called STARDIST, STARDIST. It is used to be one of the most it used to be one of the state-of-the-art nuclei cell segmentation model. So we can easily replace that cell segmentation, nuclei segmentation model to a cell segmentation model. So in that case, we can also include the cytoplasmic information. At this moment, we also have features of cytoplasmic features, but we simply just by dilating the nuclei segmentation mask to its neighbor by including that neighbor information. Yes, so basically it depends on what semantic segmentation model we used in our pre-processing, but it's definitely doable, yes.
Interesting. So the cytosol boundaries are difficult, right? Because you don't know where the cell ends, so you want to expand the nuclear mask instead. Okay.
Yes.
Wonderful. Are there any other questions from the audience? Feel free to chat or unmute yourself. In the meantime, I will ask a quick question. So you remember the, I think, .NET model, the very first image search model that I think came out right early days of this AI. And then they actually now can kind of tag a cat as a cat, right? A car as a car, right?
Yep.
So from those days to your pathology search, right? What do you think the transformation right now in the field? What's our current advantages compared to early days of net models?
Yes, so I think it's a great question. If I understand correctly, the question is how we see the differences between that basic vision language model, just like GPT-4o we released, compared to a much more fine-tuned model for pathology. I think that one of the most differences is GPT-4o, that kind of vision language foundation model, has been trained on a lot of public data. And those data, like cat and dog, they have a lot of labels. And labeling such kind of image is really is relatively cheaper than annotating the medical images. So we're actually facing the difficulty of recruiting experts to annotate pathology or medical knowledge. So that is a really challenging thing. And that's why I would comment that vision language model for pathology is sort of way behind the vision language model for other type of data. So this is why my understanding. But with that limitation introduced, I also see a lot of opportunities. As we mentioned, when we think about in the history how we train an image classifier, back into 2014, when Dr. Kai-Ming He introduced residual neural network, demonstrating the ability of deep learning network actually works than a shallow neural network. People start training their binary or multi-class classifier on the ImageNet. And that ImageNet data has a carefully labeled, carefully annotated label. But nowadays, our machine learning and deep learning training may require lower quality data. We don't actually need that higher quality, well annotated data sets. We can actually use internet data or even YouTube information like YouTube videos to train the model. So that's what I can see the potential of a larger model that can be able to learn the knowledge from a less curated data source or even raw data. So that's what I can see the potential. Just like how our college students getting learned to become a attending pathologist. We learn from the textbook, we learn from the video lectures, we learn from the classroom, we learn from shadowing with senior pathologists in signing out the cases. We're learning from the environment that requires no annotation. And in the future, I think the AI model can also facilitate the same sort of education. The AI model can also learn the medical knowledge by shadowing a clinicians as well. So that's my hope, yes.
That's very exciting. And also these pathology images, they have some guessed diagnosis of these images underneath, right? Yes. I wasn't sure if you made use of in your models these diagnoses. Have you used them in your models?
Yes, so the question is, there are some disagreement between pathology diagnosis.
Agreement, yes.
Yes, this is a fantastic question. So actually, people been discussing about the disagreement of pathology for a long time. Well, when we talk about pathology, actually, think about how hospital typical clinical flow goes. We have a radiology to inspect the suspicious region, but the pathology is really the ground truth to determine the disease. And just because it is the ground truth, it is also the most difficult diagnosis, in my opinion. And actually, there's a survey on Twitter. A clinician asked their colleagues, how much time do you rely on your subjective gut feeling in making a pathology diagnosis? Surprisingly, over 60% of people click they have at least used or commonly used subjective feeling in making a diagnosis. So there's a lot of disagreement and intra-observer variability in making a diagnosis. Not even mentioning the pathology diagnosis criteria is also evolving over the years, right? So there's also challenging parts. In terms of that challenging thing, I think there's currently no perfect solution for that. Actually, even the ground truth is not really the ground truth.
Exactly.
So
exactly, you made a very correct, absolutely spot on point. The ground truth often, again, I don't mean to hog this thing. Yep. This is your time, but the ground truth is often built on consensus, and you don't need a consensus when you know what the answer is. So there's some cases that are self-evident, It's a biological continuum. You're artificially drawing lines to make it into binary coefficients. So go ahead. Sorry.
Yeah. Yes. So so I think just as Sunil mentioned, it is really challenging, and our ground truth is based on consensus. So I think currently this is a really understudied field, and hopefully we can find a perfect solution for that. Maybe retrieval augmented generation could be a useful tool. Could be, yeah. Or like retrieving the case report in previous literature to that is at least something what AI can do to assist the diagnosis process.
Wonderful. Are there any other questions? I know that we keep going on the discussions, but it's almost 3:05. In the interest of time, I think let's thank to the Dr. Huang for this fantastic talk. Let's clap for the digital and also.
Thank you so much.
Thank you again for sharing your insights. I think this is a future vision. We'll share this talk right away with the public. I know a lot of people will be interested in and reading your both papers that you talked about today. And also we look forward to your future endeavors, right? After your training there.
Thank you. Yeah.
Wonderful. Then thank you everyone for participating. Before we close, I'd like to announce that on the May 31st, we will have Dr. David McKellar from New York Genome Institute, and he's going to talk about illuminating transcriptomic dark matter with new spatial technologies. And with this, thank you, everyone, and have a nice weekend, and hope to see you in 2 weeks.
Have a lovely weekend.
Thank you, Dr. Ram. Thank you, Sunil.